right? So I just want to conclude this computing section with a sort of quick mention of two quantum algorithms. There are indeed practical problems that can be solved efficiently using a quantum computer, and two such classic problems which actually brought the idea of quantum computing to the limelight is the quantum search algorithm and the quantum factoring algorithm. So searching through an unsorted database of size n requires order n operations on a classical computer, but quantumly this can be done using just square root n operations. This is using what's called the Grover search algorithm, and so a quantum computer offers a quadratic speedup over a classical computer as far as searching through a database is concerned. The other important problem where the quantum computer offers a speedup is that of factoring a number into its prime factors. So if I have an n-digit number and I want to factorize it into its prime factors, then a classical algorithm requires n log n operations, but a quantum algorithm requires only log n squared operations. So you see you have gone from n to log n, which is an exponential speed up, right? And as n becomes larger and larger, as the number that you wish to factorize becomes larger and larger, this speed up becomes more and more important. Factoring is an important problem, as we'll just see in the next slide, from a cryptographic point of view, and hence the idea of a quantum factoring algorithm offering exponential speed up really drew a lot of attention, and this is why a lot of people start getting interested in the idea of quantum computing. So why is factoring important? Why is prime factoring important? So I'd just like to tell you a little bit now about cryptography and in particular about quantum cryptography. But I'm going to lead into it by first talking about a classical cryptographic idea and why prime factoring becomes important. So one of the important tasks that we'd like to do in cryptography is the idea of public key cryptography. So I have two parties, A and B, who would like to communicate with each other over a public channel, right? And what I mean by a public channel is a channel which is insecure, which is susceptible to eavesdropping, right? Which is susceptible to hacking or eavesdropping. Is it possible for these two people, A and B, to be able to share or generate a secret message even while communicating over an insecure channel, a channel that is not private but rather public? The answer is yes, and that's the idea of public key distribution, right? And today, a lot of the communication that we do, for example, you communicate over public channels all the time, whether it's WhatsApp, whether it's email, etc. And the reason that all of this communication is secure is because of something called the RSA protocol. This is due to three computer scientists, Rivesh, Shamir, and Adelman, and this protocol was discovered in 1977. This protocol relies on the fact that it is a very hard task for a classical computer to factor a very large number into a product of its primes. In particular, if I take two very large primes and multiply them, then that to get the prime factors of that number is classically a hard problem. That's what we saw on the previous slide, that prime factoring is a hard problem for a classical computer, but a quantum computer is able to solve it exponentially faster than a classical computer. So if we had a quantum computer today, then this RSA protocol would be broken because the protocol's security relies on the hardness of prime factorization. And if RSA is broken, then a lot of the public communication that we do today over various public channels becomes insecure, right? And this is why prime factoring, the quantum factoring algorithm, gained a lot of attention, and this is also why every other company today is interested in building a quantum computer. But if quantum computers indeed are going to break the security of classical cryptography, then can we do something better using just quantum states? And that's the idea behind quantum cryptography. And I'm going to just explain over the next couple of slides a simple quantum cryptographic idea, what's called quantum key distribution. The idea is the same. You have these two parties, A and B, who communicate over a public or an insecure channel, and they would like to be able to exchange a secret message. But now they're allowed to send and receive quantum states as opposed to just classical bits. And now we can come up with a protocol whose security relies on some fundamental physical principle and not on the hardness of a particular problem, not on the hardness of a particular mathematical problem like prime factorization. This is the main idea behind this quantum key distribution protocol. A and B, these two parties who wish to communicate secretly over a public channel, can now make use of quantum states. In fact, they can make use of two sets of orthogonal states. One is the 0-1 pair and the other is the Sx plus Sx minus pair. 0 and 1 are orthogonal to each other, Sx plus and Sx minus are orthogonal to each other. But of course, 0 is not orthogonal to Sx plus and 1 is not orthogonal to Sx minus and so on. Let me first describe the protocol and then we'll understand why it works, right? So the protocol is very simple. A has to choose some random classical bit string, right? She just chooses some set of bits randomly, right? And the idea is to somehow communicate this random bit string to B and extract a secret message out of this, right? So in order to do that, A is going to send a qubit corresponding to every classical bit that she generated. And how is she going to pick the qubit state? She can either choose the 0-1 states or the Sx plus Sx minus states. So if she were to choose the 0-1 state, then the classical bit 0 would be represented by the ket 0. The classical bit 1 would be represented by the ket 1. But if she chooses the Sx plus Sx minus basis, then the classical bit 1 would be represented by an Sx minus. The classical bit 0 would be represented by an Sx plus. Now what she does is for every bit, she is going to make this choice randomly. For every bit that she has to send, she is going to pick a quantum state either from this set or from this set, and she is going to make the choice randomly. So this is one new source of randomness. There's a second source of randomness that once she has sent the state to B, B has to retrieve the classical information, and in order to retrieve the classical information, B has to make a measurement. But now B has a choice of measuring either in the sigma z basis or in the sigma x basis. And again, B has to make the choice randomly, right? And at the end of the protocol, they compare their basis choices. Whenever B's choice of measurement basis matches with A's choice of basis, they retain the classical outcome. When the choices don't match, they reject those classical bits, and hence they end up with a secret key. Well, how does this work? Note that I now have two different basis sets, one corresponding to a sigma z operator and the other corresponding to a sigma x operator, right? So first of all, unlike the classical case, I am now dealing with non-orthogonal states. Classically, 0 and 1 are always orthogonal states. They're always distinct, distinguishable states. But quantumly, I have states that are non-orthogonal. Like I said, 0 and Sx plus are not orthogonal. You take the inner product, you know that you get a 1 over square root 2. Similarly, 0 and Sx minus are not orthogonal. Their inner product is again a 1 over square root 2. Ket 1 and ket Sx plus are not orthogonal. Ket 1 and ket Sx minus are not orthogonal. So you have now a set of 4 states where across bases they are no longer orthogonal, they have a non-zero inner product, and because of this they cannot be perfectly distinguished. The state 0 and the state Sx plus cannot be perfectly distinguished. I cannot devise a quantum measurement which will always tell me whether the state that I have is a ket 0 or a ket Sx plus without error, right? So just to dwell on this a little bit more, remember that Sx plus is a superposition of the form 0 plus 1 over root 2. So when I measure Sx plus in the 0-1 basis, what am I doing? I'm measuring the plus half eigenstate of the sigma x operator in the sigma z basis, right? I'm measuring what is an eigenstate of one operator in a different basis, in the basis of a sigma z, right? Then what do I get? Both outcomes are equally likely because Sx plus is an equal superposition of 0 and 1. It's 0 plus 1 over square root 2. So the probability of getting outcome 0 is a half, probability of getting outcome 1 is a half. So every time I measure, I will randomly get the outcome 0 or the outcome 1. And now you understand why I cannot distinguish these two states perfectly. Because I either have to measure in sigma z basis or I have to measure in sigma x basis. If I measure in sigma z basis, half the time I'm going to get ket 0 and half the time I'm going to get ket 1. On the other hand, if I measure ket 0 in the sigma x basis, similarly, half the time I'll get the outcome plus half and half the time I'll get the outcome minus half. So both outcomes become equally likely, or in other words, you are uncertain about the sigma x, about the spin value in the sigma x of the sigma x operator when you measure in the sigma z basis, right? So such operators are called complementary operators, or such properties, right? The spin along sigma z and the spin along sigma x, right? They correspond to complementary properties. What it means is these eigenstates, they are eigenstates of sigma z and sigma x, and remember these are two operators that saturate the uncertainty relation. So if you have information about one of these operators, say if you have information about sigma z, which means if you are in a sigma z eigenstate, then you are maximally uncertain about the sigma x eigenvalue, and if you are in a sigma x eigenstate, you are maximally uncertain about the sigma z eigenvalue. That's the example I just mentioned here. You are in a sigma x eigenstate and you are maximally uncertain about the sigma z eigenvalue because both outcomes are equally likely. So this is what the uncertainty principle does. It places a fundamental limit on the precision with which such operators can be measured, right? And so now let's revisit the QKD protocol, right? Here's a sample protocol. So A chooses some classical bit string like this. Corresponding to every bit string, A chooses a basis, right? So for the first bit string, she chooses the Z basis, which means the classical 0 is encoded in a ket 0. For the second classical bit, again she chooses the Z basis, which means the state that she will send is the ket 1. For the third classical bit, she now chooses an X basis. So the state that she will send is the Sx minus state. The fourth classical bit, she again chooses Z, so the state will be a ket 0 and so on. So you can populate this table now, right? So the qubit that A sends could either be 0, 1, Sx plus or Sx minus, depending on two things, depending on the bit string, depending on the basis, right? Now, B is receiving all these qubit states. B has to measure in order to retrieve this classical information which is in the first column, rather the first row, right? But what basis must B measure in? B doesn't know. So B is going to make a random choice. Now look at the first instance. B's random choice coincides exactly with A's random choice. So if B measures ket 0 in the sigma z basis, then the outcome is going to be 0 and their classical bit values will match. So this is an instance where they will get a correlated classical bit, and so this contributes to the secret key. But the second instance, B's basis choice is different from A's basis choice. So the uncertainty principle will now tell you that whatever outcome B gets is invalid because both outcomes are equally likely. When I measure ket 1 in the sigma x basis, I'm equally likely to get a plus half or a minus half, which means I'm equally likely to get a bit 0 or a bit 1 outcome. So this will not contribute to the key. The third instance, again, their basis choices match. So once again, you will find that the classical bits are correlated. So this again will contribute to the key. So you can sort of look through this table and see that whenever the classical, whenever their basis choices match, the classical bits are correlated, and hence in these instances, without really communicating the classical bit, but rather by making a random basis choice and by sending a quantum bit, they have managed to end up with correlated classical bits, right? And so they have generated a secret key 0101. So though they started with, let's say, a 7-bit string, they ended up with a 4-bit string, which is now secret between them. Why is it secret? We'll see that in the next slide. So I just want to mention that this protocol is called BB84 in honor of its founders, Charles Bennett and Gilles Brassard, and it was originally presented at a conference held in Bangalore, interestingly, in 1984. So why is this kind of a protocol secure? What makes, why does an eavesdropper not have access to information in this protocol? Well, first of all, the eavesdropper does not know the basis choices, right? In the end of the protocol, A and B will match basis choices, right? A and B are going to communicate and write down their basis strings and identify those locations, these locations which I have marked here, identify the locations where they have the same basis. But the eavesdropper doesn't have this luxury, right? So the eavesdropper does not know the basis that was chosen by A to encode the information. Neither does the eavesdropper know the basis chosen by B to make the measurement. So there's no way for the eavesdropper's measurement outcome to be correlated with either A or with B perfectly. And because these are complementary properties, the uncertainty principle ensures that if the eavesdropper chooses a wrong basis to measure, then the eavesdropper does not have any information, right? And furthermore, any operation that the eavesdropper performs must disturb the quantum state. The act of measurement collapses a quantum state. And so this disturbance can actually be detected by A and B. And so the conclusion is that the amount of information that's accessible to the eavesdropper while remaining undetected is negligible, right? And this is what makes this kind of a protocol secure. The security essentially comes from two physical properties: the uncertainty principle, which ensures that unless you know the basis in which the information was encoded, you don't have access to that information. And secondly, in trying to access the information, you must necessarily disturb the quantum state. So the uncertainty principle and the fact that the measurement disturbs the quantum state ensures that a quantum protocol for public communication can be made secure. So is all of this just in theory, or can one do this in practice? Well, today we have such quantum key distribution kits being sold by companies. This one is a kit made by a Geneva-based company called ID Quantique. The box on the left can be thought of as one of the two parties A. The box on the right can be thought of as the other party B. They're communicating using polarization states of light. The qubit that they're using is polarization, and that's why they have a whole bunch of optical fiber here through which they communicate. And of course, there's a lot of control electronics and everything involved here, but you can also sort of make out the laser source and so on that they're using. And this is basically QKD in action. Two of us can buy these boxes, use quantum states to communicate securely. What about quantum computers today? Well, this is what today's quantum devices look like. The one on the left is the IBM Q1 processor, which has about 50 qubits. The one on the right is Google's processor, which has about 72 qubits. Well, where is the processor really? So Google's chip, the so-called bristlecone chip, is sitting out here, right? So the quantum chip itself is obviously extremely small, but the rest of it is basically a whole lot of control electronics and also this big dilution refrigerator which is needed in order to preserve the qubit states. So the key challenge today in realizing this idea of quantum gates and quantum circuits is the fact that qubits are susceptible to noise. Qubits interact with the environment. All that we were talking about is isolated qubits, right? We didn't talk about interacting with the environment. So that causes noise, that causes the qubits to decay. And hence the main challenge is to be able to build quantum gates and circuits which are resilient to noise. So I stop here, and if you would like to learn more, then I suggest chapters 1 and 2 of the book by Nielsen and Chuang called Quantum Computing and Quantum Information. Essentially, that will go over many of the things that I mentioned, and it also gives you some general history and context to the subject. I hope you had fun listening to the lecture. Thank you.